I am called Bertrand Jamuto. I am an aspiring solutions architect and cloud engineer. Here is my contact information. And today I'm going to be presenting a three-tier web application in AWS. But before we dive in, we really will need to understand what a three-tier web application is all about. Now, a three-tier architecture is a design pattern that divides an application into three layers. We have the presentation layer, the logic layer, and the database layer. Now, the presentation layer is where the user interacts with the application. Typically, this would be the UI of your website or your mobile application. And the logic layer or app layer is where the processing, calculations, and manipulations happen. And the database layer is where your information is stored. Now, this is our architecture as a whole, and this design is going to follow what we call the six pillars of the well-architected framework of AWS. And we will be looking at the six pillars in question, which are number one, operational excellence, and this focuses on running and monitoring systems to deliver value and continually improving processes. And it involves automating changes, responding to to events, and defining standards. Now we have reliability, which is our second pillar, and this deals in the ability of the system to recover from infrastructure disruptions. And it deals in concepts like fault tolerance, high availability. And the third pillar we have is security, which is very important. And this deals in the need to protect data, systems, and assets while delivering business value through risk assessment and mitigation strategies. And under security, we'll deal with things like identity access management, data protection, incident response, and compliance. And the fourth pillar is operational efficiency. And this pillar focuses on using computing resources efficiently to meet system requirements and maintaining efficiency as demand changes. And it covers areas like selection of compute resources, caching, and um, monitoring. We equally have the pillars of cost optimization, which we are not going to really see here, and sustainability. Cost optimization deals with the need to avoid or eliminate the unneeded expenses in the cloud and involves choosing the right resources, analyzing spending, and using managed resources or services to reduce operational overhead. So here is our architecture, and basically our architecture, we have a user initiating requests to our application, and the point of entry of our application is this elastic load balancer, in which case it is we're using an application load balancer which forwards this client traffic to the instances uh, of the web tier. Now, the web instances are running on Nginx web servers that are configured to serve a React.js website and redirects API calls to this internal facing load balancer. The internal facing load balancer now forwards the traffic to the app tier instances, which is written in Node.js, and the application will now manipulate the data and send them to the MySQL multi-AZ database, which then returns an answer to the client on the web tier. Now, we need to understand the underlying infrastructure of our application, and the underlying infrastructure consists of a VPC, and very soon we'll be moving to the console where we would see more about the VPC. So this is a VPC, and a VPC simply means a virtually isolated network that permits us to launch AWS resources, and this gives us control over networking, security, and it gives us that added advantage that a traditional data center doesn't have. So we have a VPC with a well-defined IP range and two availability zones. And in this case, I'm going to use US East 1A and US East 1B as my availability zones. And we have six subnets. And the reason why we have six subnets and not three subnets for each tier is because we are deploying our architecture in a second availability zone to improve fault tolerance and provide resiliency. So we are going to have um, two public subnets in the web tier, two subnets or private subnets in the app tier, and two private subnets in the data tier. And um, let's move over to the console. So this is our VPC, and our VPC is the three-tier demo VPC, and it has this is the defined range of IP addresses that I gave it, 10.0.0.0/16, and /16 is our subnet mask. This implies that the first 16 octets of our IP address is going to be for the network addresses, and the next 16 octets will be for our host IP addresses. Now the subnets, we have six in number, and a subnet is simply a logical grouping of IP addresses within an availability zone, and it permits us to launch resources such as instances and databases. And we have two public subnets, one for each one in the web tier of each availability zone, and this subnet, to be able to access internet, this subnet has a route table, and this route table has target as the internet gateway, and which is what sets a public subnet from apart from a private subnet which has a target as the NAT gateway. We'll get to that shortly. So we have a public subnet also in the second availability zone, and we have our private subnets in two in each availability zone, one for the app tier and one for the database tier. And let me click here to see. In the private subnet, the route table associated to it is a NAT gateway. And what differentiates a NAT gateway from the target here is a NAT gateway, and what this means here is that the NAT gateway is going to be the target of our traffic. That means traffic that is coming from the app tier instances are going to be directed towards the NAT gateway, which would then send it to the internet. And the NAT gateway is simply a gateway that is placed in the public subnet of our VPC and permits the resources of a private subnet to initiate connection to the internet, but does not allow the internet to initiate connections to it. And this is very important for security purposes. And the reason we might need it to those private subnets resources to access internet could be to update servers, to download and install dependencies on our EC2 instances. So this, we would go to the route tables, and we have three route tables in number: the route table of the public subnet, and um, a route table or a private route table for uh, the private instances or the instances of the subnet, private subnet of the app tier of AZ1 and also that of AZ2. Now the subnet uh, is configured like this. It has a destination and a target, which simply means that the the internet coming from our web tier EC2 instances are going to be directed to our internet gateway, and the internet gateway is going to send it to the internet. Meanwhile, for the private uh, route tables, we are going to have the target as our NAT gateway, and the NAT gateway is going to provide us a unique IP address that is placed in our public subnet, through which internet or traffic from our private EC2 instances are going to be directed. And we have a series of security groups. Uh, we have a total of 5 security groups: one for our internet facing load balancer, another for our web tier EC2 instances, another for our internal facing load balancer, and another for our private EC2 instances, and another for our databases. Now let me click into one of these to see the details of a security group. And a security group has inbound rules, and security groups are basically virtual firewalls. And each security group, this security group here is configured to allow HTTP type traffic on port 80 to get to our EC2 instances. And the source of this is for our web tier security groups, would be the security group of our um, internet facing load balancer, and also an entry for my IP address so that I can be able to initiate request. So let's, apart from these, the security groups of the others, well, so let's say for the internal load facing load for the security groups of the um internal facing load balancer is going to accept traffic from, let's see, it's going to accept traffic from our web tier, the security group of our web tier instances. So the flow of traffic is from uh, the security group of the internet facing load balancer to the security group of our web tier instances to the security group of our um, internal facing load balancer to the security group of our private EC2 instances, and then to the security group of our MySQL Aurora database. Now let's hop on to our EC2 instances, and we have 6 EC2 instances currently running. And this one, two, okay. So 6 EC2 instances that are currently running. I terminated one earlier on. And these EC2 instances, I'll enter the web tier EC2 instance. The web tier EC2 instance has a public IPv4 address assigned to it. And for us to test if this connection or if it is rightly configured, we need to copy this and place it in our web server, in our browser. Okay, so we're able to reach our servers through the IPv4 address of our web tier instances. Hence, the configuration is rightly done. So in creating our EC2 instances, we have to launch instances here, and we need to choose our OS, which is Amazon Linux 2, instance type T2 micro. We are going to proceed without a key pair, and we're going to choose our 3-tier demo VPC. And for the web tier, we choose the public subnet of the web tier AZ1. And since it is a public subnet, or a public I or the instances of the public subnet, then we are supposed to enable it to auto assign a public IP in order for us to be able to connect to the servers. And the security group, we are going to choose that of the web tier EC2 instances. And then here we are going to choose add an IAM role to it. And this IAM role, which is a 3-tier SSM role, is simply the systems manager IAM role, which permits us to be able to connect to the EC2 instance. So here I'm going to go to the IAM console right now, and find this role. Okay, 3-tier SSM role. Now, this SSM is simply the system session manager, and the system session manager is a fully managed AWS service that provides a secure and verifiable way to manage and access your EC2 instances, on-premises instances, and virtual machines through an interactive shell. And it prevents us from the need of using SSH keys or key pairs. Hence, it really helps in enhancing security and simplifying instance management. So to each, it attaches Amazon SSM managed instance core permission. And let's see if we can be able to access our EC2 instance using session manager. Okay, session manager, connect. So we are connected to our EC2 instance. Let's try to change the user. EC2 user. Let me ping this to check if it's connected to internet. Okay, so there are data packages being downloaded. So this means that our EC2 instance is correctly is accessible to internet. Now to create an auto scaling group, we need to create an image, and an auto scaling group is, we'll get to that. We need to create an image or an AMI of the EC2 instance, and an AMI is simply a master image of our EC2 instance that contains the software configurations necessary to launch an instance, and the components are the operating system, the root volume, and launch permissions. From there, we create a launch template, and the launch template simply stores the configuration details needed to launch the EC2 instance. And components are the AMI ID, key pair, security groups, instance types, type of image, volumes, network settings. And we have 2 launch templates here, that of the web tier and that of the app tier. We equally have we equally need to create a target group, and a target group is simply a group of EC2 instances that the load balancer will direct traffic to. And in this case, they are going to be the the EC2 instances of our public subnets. And for our load balancer, we would need to create our load balancer, and a load balancer um, is going to distribute traffic across multiple targets such as EC2 instances, IP addresses, or containers. And in this case, there are three types of application of load balancers in AWS, and there is the application load balancer, the network load balancer, and the gateway load balancer. In this case, we are going to be using the application load balancer because the type of traffic that we are using here, or we are letting in, is HTTP type traffic. So this is our internet facing load balancer, and it has listeners and rules, and this simply means here it simply means that it is going to allow HTTP type traffic on port 80, and it's going to forward this traffic to the target group of our web tier, which we earlier defined as the instances of the web tier. And now the auto scaling group. The auto scaling group is going to consist is Auto-scaling groups are simply going to ensure that we have the right number of EC2 instances available to handle the load for our application. And we have two auto-scaling groups in this case, the app tier auto-scaling group and the web tier auto-scaling group. Let me go to the web tier auto-scaling group. Before I get there, let me try to terminate an instance. By terminating the instance, I am expecting that uh, the time it gets terminated, the auto scaling group is going to spin up a new instance for us, but we'll get to that terminating. So in creating our auto scaling group, we would need to choose our uh, auto scaling groups can scale depending on different type of policies. We have the dynamic scaling policies, and which allows the auto scaling group to automatically adjust the number of instances based on demand. And you have the scheduled auto scaling, and it allows you to scale your instances based on a schedule. And in this case, we didn't use any policies for the scaling, but we set our minimum, maximum, and desired capacity of EC2 instances to be 2. This means that at every point in time, there is going to be a minimum of 2 instances running. And uh, to create our auto scaling group, we need to choose the launch template, the and attach the load balancer to it. And our auto scaling group does health checks. It performs health checks so that to ensure that our EC2 instances are running correctly. For example, if an instance fails a health check, the auto scaling group can automatically terminate the unhealthy instance and launch a new one to replace it, which is something that the load balancer equally does something like that. It does health checks, and the load balancer simply directs traffic to only the healthy instances. Now we said that the internet facing load balancer is the entry point for our architecture. So if we go to the internet facing load balancer and copy the DNS of it to and paste on our browser, then we should be able to connect to it. Okay, so we're connected, and let's see if we can add any entries into this. 650 candies. Okay, so I've been able to add entries to this database, which means that our architecture is entirely set up correctly. So we would go to our database, RDS, and in this case, we chose an Aurora MySQL database. There are several other kinds of databases. You could equally have RDS. We have Postgres and the rest, but we chose Aurora in this case because the read replica can easily be promoted to a standalone instance if the primary database fails. So in this case, we can see that we have a writer instance and a reader instance. The writer instance is our primary database, and the reader instance is our read replica. And a read replica is simply a backup. And if this primary database fails, then it is going to spin, the read replica is going to be promoted to a full standalone instance. And the security group of our database is the database SG, which we configured earlier on to only accept traffic from the security group of the private EC2 instances of the app tier. Okay, so this brings an end to our design and architecture of the three-tier web application. But I think uh, there are things that could be improved on our architecture in order to make it more efficient. And first, we could start with improving on the security. On the security side, we could implement the use of a web application firewall in front of the application load balancer to protect it against common web exploits and vulnerabilities. Also, we could use AWS Shield Advanced for to mitigate DDoS attacks, as well as to use um, a network access control list at the level of the subnet to control and restrict traffic flow between subnets and the tiers. We could also improve on performance optimization by leveraging the use of a content delivery network with AWS CloudFront to cache and serve static content closer to end users in order to reduce latency and improve responsiveness. Equally, we could use caching solutions like Elasticache as an in-memory data store to offload read operations for the database. We could improve on operational efficiency and automation with the use of by implementing the use of infrastructure as code tools like AWS CloudFormation and Terraform, which is a third-party provider, to automate the provisioning and management of the entire infrastructure, because it's a lot of operational overhead to provision all these resources, and using these uh, really solves this problem. Also, we could improve on high availability and fault tolerance by deploying the application load balancer and internal facing load balancer or internal load balancer in multiple availability zones for increased fault tolerance. And we could equally implement the use of Amazon Route 53 for DNS failover and health checks. to ensure a seamless failover to a secondary region. Also, um, to improve cost optimization, we could use um, tools like AWS Trusted Advisor, AWS Budget, and AWS Cost Explorer to monitor and optimize cloud spending. And we always need to back up our infrastructure or data. And for that, we could explore the use of S3 to store for storing static content, logs, backups, and other application data for durability and cost effectiveness. And we could also set up monitoring and observability with the use of AWS CloudWatch for comprehensive monitoring of resources, metrics, logs, and events across all tiers. So this is going to be the end of the three-tier architecture design, and have a good one.